hear me? Okay, let's get started. Hello, everyone. Welcome to lecture 8 of computer architecture. Today, we're going to cover an exciting topic, memory latency, which is a broader topic which we can consider as latency in different components in the computer system. Has been actually one of the hardest problems to solve. And in order to essentially hide the latency, tolerate high latency in our systems, we've been adding a lot of cost and complexity to our systems. We're going to see a lot in the beginning. I'm going to provide some motivational study about why we need low latency and why is the very hard problem. And then at some point, we're going to move to different techniques that we can fundamentally reduce latency, which these techniques actually can be very much important as they can basically solve the core problem. In many, many cases, because of the high latency that we have in our system, we design different techniques. Think about cache hierarchy, for example, that we have. Think about prefetching. Think about high costly interfaces that we have in our systems. I mean, all of them are there just to provide enough parallelism such that you can hide latencies. So if you don't think about solving the core problem, you're going to be still working on solving the latency hiding problem, which might not be efficient enough. So at some point, we really need to also change, maybe not completely, focusing on only latency, but essentially reducing latency also should be one of the core objective in our system. So probably doing that together with parallelism, we can get to much better systems. Okay, so remember about these 5 major research topics that we have in our group in Safari, and fundamentally low latency and predictable architecture is actually one of the important one. So having low latency architectures is important because there are a lot of applications that they are latency bound. There are also many applications that you don't see them as latency bound, but in order to hide latencies, actually, as I said, you're adding a lot of complexity to the system. So lowering latency in general is very much important. At the same time, also, there are some systems that you don't necessarily care about how fast and how quickly you do things, but you want to make sure that things are predictable, as we also discussed a little bit yesterday. So predictability is also another important metric, which is important to consider. And there are also some systems that you want to have low latency and also be predictable. So think about it, because satisfying both, having low latency and predictability, is very much important for some systems. And essentially, we want to motivate this having low latency architecture as basically solving the hardest problem. There are many, as I said, many problems in our life in different domains that they need to, when you want to need to solve them, they call for actually low latency computation. And without having low latency computation, people have tried to, to hide latencies, to mitigate latencies, high latencies, by adding a lot of parallelism, by adding a lot of threads, let's say, deep cache hierarchy, adding, making caches bigger and bigger, adding a lot of, let's say, cache optimization techniques, different latency hiding techniques, essentially. However, we should not forget that the core problem actually was there because the higher latency, the longer latency. And it's important to solve that such that we can enable also many, many other applications. So I'm going to flash some slides without making very exact connection, but you can think about how low latency architectures can help solving many important problems. Here's also another example in genome sequencing analysis, which I'm going to also show later. That essentially many of them are, in order to make the analysis real time, you do need actually low latency architectures. Also, we were discussing just before the lecture that in many of these genome sequence analysis, people need to provide privacy, And since usually in the lab, when you want to do computation, the computation power you have there is not enough for the latency that you are targeting. So time to time, people have to basically offload the computation to a server and ensuring that server, does not cause, basically can ensure privacy for you is another big challenge here. So by designing architectures that they are much lower latency, we can also potentially enable real-time analysis, as well as also potentially enabling high-performance edge computing, which can be very useful for privacy preserves, for example. So yeah, here's also another interesting analogy about brain, because we should be thinking how we can get insight from this kind of this brain, this amazing computer system to solve the problems. And I don't think actually the way that we are using neural networks and artificial intelligence is actually the way that the brain is working necessarily. And there are a lot of inefficiencies in our computer systems, and understanding how brain works actually can provide a lot of insights to our system to make it much, much higher performance. I like also to use this analogy from Maslow. Does anyone know about this analogy? Or have you seen this human hierarchy of needs from Maslow? Yes. Yes, Said, okay, yeah. So yeah, essentially he's an American psychologist. And basically the analogy was that for human, the first, the required need is actually things like food, water, and you need to make sure that you provide that essential need. And after that, you can also take care about safety needs like security, safety, and so on and so forth. So we can also think of similar analogy in a computer system, even though at some point you're going to see that it's not a perfect analogy because it's making decision, what to prioritize is not really easy here. But should we, for example, consider energy is at the bottom of this analogy, is at the bottom of hierarchy? Because if you don't have energy, essentially you cannot execute anything, right? So you don't care about the security and safety of the execution also. Or should we consider robustness, as the first, or robustness and energy together as the first requirements, So it's very much interesting, and there are a lot of also debate on it. You can also think about it. But maybe low latency is the most important thing here. Of course, it has a little bit joke to it. But the reason I'm talking about low latency here is that essentially if you can provide high speed and low latency computation, even if you have very low energy, you can use that low energy to do computation because you're fast. Or for example, if your computation is so fast, you don't necessarily care that if your computation is robust at every time. So you do the computation fast enough, and then you quickly check. And then if things are not correct, you just redo the computation. And actually, if you know about some domain, like for example, in quantum computing, actually, that analogy has been used in some cases. That in many cases, actually, the computation is not accurate. But since each computation is so fast, people try to do the computation and then quickly check, and then do another, and after some time they converge to the correct response. Of course, that cannot be applied to many, to the general purpose applications, but there are some applications that can benefit from that. So essentially, my point here, which has a bit also convoluted with some joke, is that if you have a speed, maybe you don't care about anything else, or you need a speed at all levels, essentially. And then the analogy ends here. So, okay. So challenge and opportunity for future. Essentially, we need fundamentally low latency computer architectures. Here is also a talk from one of Professor Mutlu's colleagues from Carnegie Mellon University, from Satya. So essentially, this talk is about edge computing and how you can basically how high performance you need to make for edge computing. And essentially, this talk basically talks about many different parameters and performance metrics that you need to provide, like the high bandwidth, low latency, ensuring privacy, availability, and many other things. It's a bit surprising that, for example, we don't have energy here, but I would also add energy here for edge device, because many of these edge devices, they are operating on batteries, and you need to be low energy. But essentially, here are also some numbers from this talk. You can actually watch this talk. It's actually a very interesting talk to watch if you're interested. But there are some numbers here from this talk that, like how a human do, for example, for VR, in order to be, in order to be satisfy, the need. Face detection, for example, the latency should be lower than 700 milliseconds. Or for example, to answer that, is this sound from a human? It should be around 4 milliseconds. So these are some timing that you need to satisfy in order to, enable such techniques like in VR, for example. And this talk actually also argues that to be superhuman, essentially the human that can actually do even better than like the computer system that can do even better than human. With VR, you can think of it in a way that you can enable people to see something, that other people also can do. But you can also think about a bit more. But with VR, you can enable applications that normal human is not able to actually experience that. You can argue about the good or bad of these things, but as Professor Mutlu also mentioned several times, technology is agnostic to how people use technology. So that's another problem that you need to make sure that people behave. But essentially, in order to be superhuman and enable very interesting applications, you need to actually satisfy these timings and even actually aim for faster analysis. Also, I already discussed quickly about genome sequence analysis, that the future of genome sequence analysis is that you essentially, you have this kind of edge device, you just give a sample, you sequence, and then you analyze. This is what people are aiming for that. Are we close to that? Clearly, no. We are not there yet. So this is actually our dream from 2007, that an embedded device that can perform comprehensive genome analysis in real time within a minute, but it's still a long ways to go. So we need to provide energy efficiency, performance, lower latency, security, and essentially we have huge memory bottleneck here. And that's why actually this lecture also nicely mapped with our memory-centric computing lectures, because clearly memory-centric computing is also one interesting way to reduce latencies. When you do computation closer to the memory, closer to where you reside data, you will have lower latencies essentially. Okay, so yeah, I don't want to go over data-centric architectures again, but essentially in one of the properties of data-centric architecture is low latency and low energy data access, which can provide with low latency memory and also lower energy consumption memory. Okay. So essentially, we want to have low latency and low energy data access. And the memory latency, there are fundamental trade-off here. So I assume, I think you remember this plot from previous lectures that, or you have not seen it in this course. You've seen it, yeah, I remember that, yeah. Essentially, you remember that capacity has been increased a lot by 2 orders of magnitude until 2017 that this plot shows. Bandwidth also has been increased, but latency actually has not been improved much. So there are different reasons for that, which we're gonna also discuss it today. But one reason actually is that latency was not the main, let's say, primary metric or primary objective that manufacturers try to optimize for, which that needs actually some mindset change, you know. That's why actually this lecture in the beginning, we are trying to motivate why we need lower latency, because you really need to optimize latency as a first level metric that you consider in your system. But another issue also is that it's very hard to optimize for latency. Like things for capacity, actually, you don't need to do a lot of things. Like Moore's law actually is providing capacity for you. Like every 18 months, you can double the number of transistors based on Moore's law. So that provides you higher capacity, higher density, essentially. I'm not saying that you don't need to do anything else. You know, Moore's will do everything for you. And clearly, Moore's also has observed, the progress, and he predicted that. But basically, increasing capacity is much easier compared to lowering latency, and also increasing bandwidth. Also, we know a lot of techniques, by multi-banking, increasing the number of ports, improving the the interfacing frequency of the channel. There are a lot of these techniques that you can use to improve the bandwidth, and that's why people are also doing that. But yeah, lowering latency is not very easy. And here also another plot which provides a closer look. Like there are different latency parameters in memory, which we're gonna also see today in more detail. But there are different commands in the memory, or let's say different process in the memory, like specifically DRAM, that they are playing in role. So activation latency, pre-charge latency, and restoration latency. And you can see that in some of them actually from this plot from 1999 to 2015, activation actually has been reduced by, let's say, 27% from this peak point. However, at some point restoration latency has been reduced, but the activation and pre-charge latency actually at some point is increasing. And there are reasons for that, which I don't want to go through it now, but essentially they couldn't really improve latency much. Here's also another analysis, which we have also shown before regarding capacity and as well as also latency. So these are also another lower level parameters of latency in our DRAM, TRCD, TRC. I mean, those defines about how fast you can activate, how fast you can pre-charge activate. So these are different latency parameters, which we're gonna also see today. But by checking these numbers, you can these parameters, you can see that we don't have much differences through the different these years, essentially. Okay, so yeah, if you want to check more, you can also check this. This paper is actually very much recommended if you want to learn more about how the memory controller, for example, and the memory chip should be communicating together to essentially provide better performance and energy efficiency. So if you're interested, you can also check this paper in more detail. Okay, so DRAM latency is critical for performance. There are many applications that you need that. If I want to also give you some insight here, there are in graph analytics, we have a lot of pointer chasing. operations. So you access a memory location, and you don't know what to access next until you get the data, you decode it, and you realize, okay, the next address is, for example, memory address 1000. And then from that, you need to get it and then chase another. So that's pointer chasing actually cause a lot of latency problem for you. And you cannot easily parallelize it. And that's why actually when you run graph analytics on a processor that they are optimized for getting high parallelism, like GPUs, you don't necessarily get good performance. You get better performance still compared to CPUs, because the computation power in GPUs is massive. But if you check the utilization rate of the GPU, utilization rate of the compute units in GPU, you're gonna actually see a very low number, sometimes less than 5%, which is not good, right? So you have that many computing power, that much computing power, but you're not utilizing it. And the main reason is that the core idea of GPU is that we don't want to reduce latencies. We just want to hide latencies. There are a lot of techniques in GPUs by having thousands of threads, that you can quickly switch across different threads to hide latencies, which those techniques are actually very useful. But for some application that you can't really do that, there are certain applications, and unfortunately nowadays we have much more applications in the line that we cannot hide as a result of lower arithmetic intensity, as well, and also more irregular memory accesses. But yeah, essentially you cannot benefit from that latency hiding techniques that people have been using a lot in GPUs. So long memory latency is a performance bottleneck for these applications. And also, interestingly, new DRAM types, they increase latency. Here's an analysis that we have done some time ago, and I'm gonna go over it very quickly. So we wanted to study workload DRAM interactions. So manufacturers are developing many new types of DRAM. And we know that the DRAM limits performance and energy improvements. But there are a lot of different types of DRAM and interface in the market. And essentially, we wanted to see how the application would behave using different memory types and with different interfaces. So the question exactly is, so which DRAM type works best with which application? So it's difficult to understand intuitively due to the complexity of the interaction. The problem, this kind of analysis you cannot really do with real system, because so the memory, when you want to do it, the memory controller is actually optimized, or you can connect certain memory to that processor using the memory controller. So memory controller is actually on the CPU chip, so you cannot change it essentially. So if you want to test different memory components or different memory types for different application, you need to change also the processor. And once you change the processor and different system and having another main board, so a lot of parameters are changing, and then you cannot really, understand your results well. So this kind of analysis is very much enabled by using simulations, and that's why we use, our Ramulator tool to do this wide range analysis. So we tested 9 modern DRAM types, including DDR3, DDR4, GDDR5. So these GDDR actually very much, used for GPUs. It's a specific kind of DDR which used for NVIDIA GPUs. HBM, high bandwidth memory, HMC, and also low power DRAM interfaces which used for mobile devices also, for example. So we tested all these. And basically, we compared to DDR3, and we observed that, for example, DDR4, it actually increased latency compared to DDR3, or GDDR5 increased area and power compared to DDR3. And that's true also. Like in GPUs, again, I use actually example of GPUs because I have worked on GPUs for a long time. So I know that GPU kind of by my heart. So I can actually use that a lot from my examples. But yeah, exactly. In GPUs also, you use the GDDR5 and also other versions, GDDR6, GDDR7, I guess, and also different HBMs. So they provide higher bandwidth for you because that's the need you need there, So GPUs are optimized for the application that you can parallelize your memory accesses nicely to different banks or different memory channels, such that you can feed data nicely to your huge, massive SIMD pipeline that you have. So the effectiveness of this pipeline is actually very much dependent on how much you can feed data to the processor with high bandwidth. But you don't necessarily care about how fast you get the data, as long as your latency is not terribly bad. Like if your latency, for example, is in terms of, let's say, hundreds of nanoseconds, you don't care much. But if your latency is going to be something like 1,000 nanoseconds or even more, you're going to see that many of these threads are actually waiting for the data and they cannot operate, which is happening a lot in graph analytics, which I mentioned. Yeah, so we tested the different memory modules in HBM, HMC, and also other DRAM type like wide I/O. Some of these actually DRAM types are not anymore in the market, like HMC, for example. I think wide I/O also is not. But basically, that moment we wanted to do this compressive analysis. So let me show you some results. So there are a lot of details in this paper, which we don't have time to go over it. But the one of the results that I want to focus on it is basically the need for lower access latency, which is for performance. So new DRAM types often increase access latency in order to provide more banks and higher throughput, which I already discussed it. And many applications can't make up for this increased latency. And that's exactly the problem that we already discussed together. So yeah, and basically you need to also think about how to lower latencies for these applications. And there are a couple of takeaways here that essentially DRAM latency remains a critical bottleneck for many applications. Bank parallelism is not fully utilized by a wide variety of our applications. And spatial locality continues to provide significant performance benefits if it is exploited by the memory subsystem. So that's probably one of the locality that you can still rely on it to improve performance. And also for some classes of application, low power memory can provide energy savings without sacrificing significant performance. Because those low power memory interface like LPDDR, they have lower bandwidth and also higher latency compared to DDR because they are optimized for low power. But there are some certain applications that you can actually benefit from them without getting bad performance results. Okay, so yeah, there are a lot more in this work, and everything is also open source, and you can check the paper as well. But yeah, we don't have time to go into detail of this work. I just wanted to use it as a motivational study for better latency. So the memory latency problem. High memory latency is a significant limiter of system performance and energy efficiency, and it is becoming increasingly so with higher memory contention in multi-core and heterogeneous architectures. And that's also another thing which we are observing a lot, as here said, in multi-core system and also many core systems, which you can think of also again GPU as a system that you have a lot of cores. So there are a lot of contention there. And basically, in many cases, you generate a lot of in-flight requests, and those requests are using the same interconnect to go to the memory modules. And even though you provide actually reasonably high bandwidths, but since you have overwhelmingly two requests, they are actually waiting for each other in different queues. And that if you can try to service these requests faster, meaning that if you make the memory faster, you should be able to potentially also reduce the depths for the queues, which in the end is going to affect having lower blocking latencies. So basically, with higher memory contention, the problem of memory latency is even much more important, which we already discussed about the need for the higher bandwidth here, and also the quality of service problem as well. You can actually, when you want to ensure that your latency of computation is lower than some amount of number, it's really important that you provide predictable performance and avoid noisy neighbors cases. You can think of, for example, there are systems which we call it heterogeneous system architecture, heterogeneous CPU GPU architecture, that they have CPU and GPU on the same die. And so you potentially you use CPU and GPU together to run your application. So the problem is that usually requests from the CPU is much more latency sensitive, but the requests from the GPU are more or less like they are less sensitive, latency sensitive, and they are more bandwidth sensitive. So when you run these two together and they're sharing the same interconnect and also the same cache hierarchy, you're gonna see that GPUs actually can cause a lot of latencies to the CPU request, because if you are not careful, people have tried to design, for example, techniques, how to manage this contention between CPU and GPU, but that's also not perfect. Essentially, having these two together, GPU can cause a lot of latencies for CPU domain, CPU applications, and that can essentially potentially also cause problem to your quality of service. Okay, and the memory latency problem increases processor design complexity due to the mechanism incorporated to tolerate memory latency. And I think we have discussed it enough, all these techniques that we have in our today's system. If you think about the out-of-order processor also, you have a lot of complexity there to hide latencies here. So here is a slide that shows retrospective of conventional latency tolerance techniques. Actually, this is a slide I think Professor Mutlu actually has used it for his PhD defense. Because I'm going to actually show also some technique that Professor Mutlu has developed during his PhD thesis, which actually was very impactful, and that work also won the Test of Time Award in HPCA. But essentially, that work also in the line of latency hiding. So if you, at some point, if you really want to do much more fundamental, you really need to tackle the core problem, which is high latency. And maybe we should start from that baseline, and then try to optimize our systems. But here, actually, it categorizes some of the techniques that people have developed for basically tolerating latency, like caching, prefetching, multi-threading, and out-of-order execution. And I think all of you are aware of all these topics, right? Question? Okay, good. So yeah, but however, none of these fundamentally reduce memory latency. Runahead execution is the one technique that Professor Mutlu has developed during his PhD thesis and have actually impacted many other works. Industry actually also used this kind of Runahead execution in the different systems, which I'm going to show. But the idea is actually quite simple. So when you have a perfect cache, you do computation, and then you get to the memory access, and you hope that it's gonna be hit in the L1 cache. So you compute, and then you have load one, and hopefully hit, and then you continue your computation. Another memory access, then it's gonna be hit, and then you continue your computation. So of course that's the perfect case. We don't want to have miss in our caches. But in reality, when you have in a small out-of-order instruction window, you do computation, and then you get to the load, which can miss in your cache. And you can still compute, because that load might not be the oldest instruction in the instruction buffer. So you can still compute and essentially retire some instructions. But once this instruction, the load, is the oldest instruction in your pipeline, you cannot retire it anymore. So you need to stop, essentially. So that's the processor has stalled for some time until you service the miss. And then when you get the data, you continue your computation, and then you get to another load, which can potentially also miss. Again, you do a little bit computation, and then you stall, and then you can compute. So that's going to be your execution time in many cases, which actually has been also has been shown by industry papers as well. Like if you check Google papers on their workloads, they have shown that like 50–60% of the time, or even more actually, the processor are just stalling. They don't do the things that they are designed for. remember that analogy, that perspective that Professor Mutlu provided, that we can ask a 10-year-old kid that if the system is working well or not. So I'm just giving that hint to remember. You remember about that lecture. So with Runahead, the way we can do is we do compute. Then we have this miss. We still continue our compute similar to previous one. But after that, when this load instruction is the oldest one, you instead of stalling, you continue execution speculatively in a Runahead mode, meaning that you continue execution, but you don't commit necessarily instruction. You just execute in a Runahead mode, which you can think of it in a speculative manner, right? Why? Because this can potentially you can reach to the next load in the Runahead mode, and you generate that memory address also faster. And so after that, so you compute, you get to this load miss, and then you move to the Runahead mode. You continue in Runahead mode, and then you hopefully generate this load 2 miss. And you continue actually in the Runahead mode until you get the result back for this load 1 miss. Then you essentially, you need to flush the pipeline and return to the checkpoint, which means that you start the computation before the load 1. So now you start accessing that memory, and then you're going to be is a hit because you already have the data. And then you compute. But fortunately, hopefully, when you get to this load 2, it's already available, and it's going to be hit in your cache. And then you can compute, and it's going to be your safe cycles. Make sense? Yes. Yeah, that's a limitation. That's of course a limitation, but basically this idea has shown that this can be useful in many cases. You can actually come up with some applications, some corner cases that potentially the effectiveness of the technique is going to be limited. But in general, actually, from this paper and also follow-up works as well as industry works, people show that in real application we have enough opportunity for doing that. For example, this is the result from Sunrock. This company was one of the innovative actually company, but they have been bought by Oracle. And and from that moment, I don't know still what they are doing now. Maybe they don't exist anymore also. I mean, they don't exist at the at the Sun probably, but anyway. So this work also they implemented similar technique. They call it Scout. So Scout is similar to Runahead. Like when you are in a Runahead mode, you can think of it as in Scout mode. And they actually show that if you don't do that, you're going to be in the curve of red. And this plot, you show the normalized IPC, depending on also the x-axis, you have L2 cache size. But by doing a scouting, you can actually provide higher IPC, like higher performance, using similar cache sizes. Or you can also think about using this technique for reducing the cache size. So you can get similar performance, by scouting and using much lower cache sizes. So you can, for example, buy 7 megabytes of cache here. And clearly, Runahead is not that expensive. Runahead is much more lightweight compared to 7 megabytes of L2 caches. So this is, for example, an important analysis also that shows or confirms kind of results that we have provided in the Runahead paper, and which is always good, to also get similar results from the other works. There are a lot more in Runahead execution. This is the original paper of Runahead, which Professor Mutlu has done it in his PhD study. But there are also a lot of follow-up works that at some point we're going to also cover them in more detail in our cache prefetching lecture in the compute-centric part of the course. So remember that this course actually we start with memory and is more memory-centric, data-centric, and at some point we move to more compute-centric, which we will cover a lot of things about CPUs, like cache coherence, memory ordering, multiprocessor, prefetching, and through the end also we're going to cover things, a fundamental thing which is important for both memory-centric computing and computer-centric computing, which is interconnect. Regardless of what system you have, you need fast interconnect. You need a good low energy interconnect. So we're going to have hopefully 2 lectures for interconnect also through the end, which is going to be very much exciting. So you can, if you are impatient, you can check these papers and learn about Runahead. But as I said, we're going to also cover them in our future lectures. And here is also a talk from, it's actually one of the old lecture in this course in 2020. Not that old, but some time ago. And as I said, Runahead also basically this paper won the Test of Time Award in HPCA because of the huge impact in industry and also in academia that many works have done it. NVIDIA also in the work in their system, NVIDIA Denver, they actually use Runahead technique for the system. Okay. But but in the end also Runahead can be also categorized here, as one of the technique that you can actually use to hide latencies. You can actually also think of Runahead in a way that you can do prefetching, which is very good for applications that you have irregular memory accesses, because with Runahead you can actually you run the instructions to get the address for the future memory accesses. But unfortunately, none of these fundamentally reduce memory latency, and we do need techniques that we fundamentally reduce latencies. So there are 2 major sources of latency inefficiency. One is that modern DRAM is not designed for low latency, which we already discussed it a lot. So the main focus is cost per bit, which is capacity. And another issue is that modern DRAM latency is determined by worst case conditions and worst case devices. Remember about previous yesterday lecture regarding the retention time. So we try to actually refresh DRAM rows with a retention period which is fast enough to make sure that hopefully all rows gonna be refreshed fast enough. But however, we have shown, other people also have shown that the real profile is not like that. So there are a lot of rows that you can actually refresh them less frequently. So the similar problem also exists in latency. So in the DRAM manufacturers, they determine the latency, they basically determine, and also the memory controller, which try to obey these latencies. So all these latencies are determined by worst case conditions and worst case devices. So basically, much of these is unnecessary. So our goal is to reduce memory latency at the source of the problem in this lecture. Okay, let me see. Okay, so maybe I can continue and then we can take a break. Okay, so truly reducing memory latency, and so we need to see more clearly what causes the long memory latency. So there are 2 reasons which we already categorized them. The first one is about, we want, the main focus was for cost per bit. And the second reason is that one size fits all approach, which you basically determine all these latencies for the worst case. So we consider same latency parameters for all temperatures, even though we know that basically on higher temperatures, you have higher latencies, or for example, lower temperature, you can actually operate faster. The same thing for the refreshing also problem. We consider same latency parameters for all DRAM chips, same latency parameters for all parts of a DRAM chip, same latency parameters for all supply voltage levels, and same latency parameters for all application data. So we will start with the first reason, and then hopefully through the end, we also start some, discussion about reason 2, and then I think at some point we need to, continue in the future lecture next week. Okay, so I think before we move on, it's good to take a break because it's a clear cut. Let's be back at 2:15, and then we will continue. Okay, let's continue. So yeah, basically, now we want to focus on reason one, that's why we have long memory latencies, and essentially develop different techniques which can contribute to fundamentally reducing latency in DRAM microarchitecture. But before that, we need to first provide a brief overview on DRAM chip. I think you already got some background on DRAM when we were discussing about processing using DRAM. But I mean, just to jog your memory, this considers a DRAM module or DRAM DIMM, and each one has several chips, DRAM chips on a module. So here's a picture of this DRAM chip, and there are different goals. Like you need to optimize for that: cost, density, reliability, bandwidth, parallelism, power, energy, latency. And clearly, manufacturers try to optimize mostly for density and cost. They're also now trying to look at reliability also a bit. They try actually to ignore the problem for a long time, but now actually they're also focusing on it and writing papers on that as well. But yeah, essentially these are different goals, and in DRAM chip you have several DRAM banks, and essentially in each bank, I think I have a better picture later. So, so this also the sense amplifier. I think you are again aware of the architecture is cross-couple inverters that you know the simple implementation of the sense amplifier, and you have enabler to enable sense amplifier or not. So there are two stable states in sense amplifier, logical 1 and logical 0. So if essentially here when you enable sense amplifier, depending on the status of this this wire, which is considered as bitline, when it's a bit higher than VDD over 2, like a bit more than half VDD, this structure is going to be converged to VDD and 0. So that's the thing your sense amplifier does for you. And if it is the bitline is lower than half VDD, then you're going to converge to 0 and VDD. So that's the operation of the sense amplifier. And here is also another way. So if essentially VT is greater than VB, you're going to converge to VDD and 0, and also vice versa. And each DRAM cell is a capacitor, which you can have empty state and fully charged state, and then you can encode it at logical 0 and 1. So this DRAM's capacitor is actually small, which cannot drive circuits. And so essentially, that's why we need the sense amplifier. So when you activate a DRAM row, these cells are connected to the bit line. And I'm going to show you later also in a picture, but essentially each bit line also has a capacitor. So in the beginning, you're going to have this charge sharing across two capacitors. That's the first process that you have. And that process will cause that bit line perturb a bit. And then you can use sense amplifier to converge it to the stable situation. So that's why basically these cells are small, they cannot drive circuits. And also reading from DRAM is considered to be destructive. So because through the charge sharing process, which we're gonna also show later, that DRAM cell, we're gonna lose some charge or gain some charge, depending on the state. If the DRAM the capacitor is fully charged, that capacitor will lose a lot of charge. And in order to cause some perturbation in the bit line. And if it's in the empty state, then the capacitor will gain some charge. So after the sense amplifier works on it and we get to the stable situation, we actually need to wait for some time in order to restore the charge. And that's the process of restoration to make sure that we don't destroy your data when you're reading from DRAM. Make sense? Okay. Yeah, so this is the DRAM cell operation. Assume that this capacitor is fully charged. you connect it to the bitline, that bitline which is pre-charged. That's why it's half VDD. And so you connect it using your access transistor with the word line. And then once you connect it, actually, we're going to have charge sharing procedure between this capacitor and also the bitline capacitor. At this moment, actually, the sense amplifier is still disabled. So that's why we have 0 here. So bitline is actually considered as a wire here, which is not connected to any power supply, right? It just has a capacitors because of those parasitic capacitor that each wire has. But since bitline is actually long and wide enough, the capacitor of bitline is actually larger than the capacitor that you have in your DRAM cell. So that's why when you do charge sharing between this capacitor in DRAM cell and also the bitline, DRAM cell actually lose much more charge. And the bitline will gain a little bit charge because of the difference between their capacitor sizes. So that gain causes a little bit increase in the bitline voltage. And after that, you essentially enable sense amplifier. Once you enable sense amplifier, actually bitline now is connected to the power supply essentially. And this sense amplifier will basically make it, converge to the stable situation, which is VDD and 0. Make sense? Good. And after that, you need to wait until you restore the charge to your capacitor, and that's the charge restoration procedure. Okay, so we have DRAM subarray, which is the building block for DRAM chip. So here is our sense amplifier, and there are several cells that they are sharing the same bit line. And so with that, we can have they are organizing a subarray. And you can actually also add more columns to it. So you have several rows and columns in your subarray essentially. So here we are showing one subarray. And for this, you also have row decoder. So array of sense amplifier, which is your row buffer. For example, it can be 8 kilobits. Okay, and so several subarrays, actually they are organizing a DRAM bank essentially. And you're gonna also have a bank IO here. There are some global IO circuitry, which after you read your data through this sense amplifier or your row buffer, when you want to get the column address, you essentially move basically the corresponding bits or the column through this bank IO to get the data to the processor. So essentially, you apply the row address to your row decoder, and you apply the column address to your bank IO, and then you get your data out. Make sense? Okay. However, memory channel is actually we have low bits in it because of the the limitation of the number of IO pins. So the output is the IO pins here is that we can only do 8 bits. So that's why you need to actually combine different DRAM chips together in order to, for example, send 64 bits of data to the processor. So that's also the problem of data mapping that people do across different chips of DRAM in order to provide better parallelism to the processor, better throughput to the processor. Okay, and so in the chip, you also have these different, different banks. And there is this shared internal bus, which you have seen it also in row clone, that, for example, you can use this shared internal bus in order to copy data from one bank to another bank. Okay, question? Good. So for DRAM operation, essentially, you need to activate row. That's one operation, assuming that the state is pre-charged. So that's something that we are assuming here. So when the state is pre-charged, meaning that the bit line is initialized to have VDD, so everything is pre-charged. Then you activate the row, and basically activate the row. And also in the activation, you also need to remember that activation has 2 parts. So you first connect the cell capacitor to the bit line, and after some time you need to enable the sense amplifier. So all of them together consider as activation, activating the row, and then you can send read and write column command by sending the column address that you already. Because when you activate the row, actually row is, for example, 8 kilobits. So you don't want to get all 8 kilobits to the processor, right? You want to some amount of it. So that's why you will send some column address after that to get your data. And that data will be transferred to this, the global I/O and through the bank I/O. And after you are done, you should when you want to close the row, essentially you do pre-charge. By doing pre-charge, you close the row. You can actually delay the pre-charge, meaning that you keep this row open for a while. Why is that? Because you are predicting that there are going to be some future accesses that they need to be serviced by the same row buffer, but benefiting from, for example, some locality, some special locality, for example. So you can have that policy which you keep your row open for a while, and when you don't need it, essentially you close it. And closing means that you pre-charge it. But with some technique that some read disturbance problem that we're going to also read much more later, row press, for example, it's not very safe to keep your row open for a long time because that can cause read disturbance error for you. Okay, so, and there are a lot. If you want to clearly learn about all these background of DRAM, I can recommend you check this book chapter in section 2. Vivek actually has provided a lot of interesting background on how the DRAM internally works. Okay, so now that we know a little bit about DRAM microarchitecture, we can try to start focusing on reason 1 and try to improve the performance. So the first work I'm gonna discuss it, like the first kind of idea, is tiered latency DRAM. So basically, one of the reasons that we have long latency is that basically we have in a bank we have several subarrays, and essentially the latency is coming from the subarray latency plus I/O latency. So, and there are a lot of works, and from the data sheet also we can get that subarray latency is the dominant for the latency. And the main reason is that the subarray is actually the bit lines are long. So when you want to operate on that, you have long bit line, and that long bit line will cause you a lot latency. So for example, we have like in order to reduce the cost. So why actually the reason that people try to have make bit line long is that they want to amortize the cost of sense amplifier. So sense amplifiers are large units, and in order to you want to reuse the same. You want to reuse one sense amplifier across several rows. With that, you can amortize the cost, right? So that's why actually in DRAM chips, people are using several rows in subarray, which they are sharing the same sense amplifier. So usually people get to this number of 512 cells, for example. At some point, if you have too many essentially rows connected to your bit line, then the latency of that bit line is a lot, and you need also much powerful and accurate sense amplifier to operate on that. So there is actually a sweet spot, and more or less people actually get to that 512, 1000 rows in one subarray. Okay, but the problem is that with large bitline capacitance, when you have a longer bitline, your capacitor is larger, you're going to have higher latency and power consumption. So clearly, there is this fundamental trade-off between area, die size, and latency. So when we have long bitline, we have basically a slower operation. We can actually make it faster by using short bitline and basically chopping bitline, and add sense amplifiers in between. So now you have shorter bitlines. So this is clearly faster, but of course it comes at the price of capacity overhead. So there is this trade-off between area and latency. So we have done this analysis using some analytical model and also some simulations. And essentially, we observed that when you want to, so depending on how many rows you have in your subarray. So in the normal case, so we are normalizing these numbers to DRAM area. So 1 means that you're using the same subarray size, which I believe 512 rows. So with that, your latency is somewhat around 50 nanosecond. And here is your area. However, when you reduce the bitline size, meaning that you reduce the number of rows in your subarray, you're reducing the latency, but that comes at the price of larger area. In, for example, if you want to have around 20 nanosecond latency, you're going to have around 4 times larger DRAM, which shows you this trade-off is actually very strong here. So ideally, we want to operate somewhere here, right? We want to be small and also low latency, but we couldn't find that magic yet. Okay. I said all of them. Okay, so we can try to approximate the best of both worlds. In many cases in computer architecture, when you see these trade-offs, you can immediately also think about some heterogeneous techniques. Actually, if you think about our memory hierarchy, that's a very good example of heterogeneity, right? Ideally, we want high capacity and high performance memory, right? However, we cannot get that from, for example, hard disk, from storage. So then we add DRAM, and then we add caches. And by relying on cache locality, or let's say memory access locality, we are hoping that we can get, basically we're gonna be able to service most of the requests in L1 cache, which is fast enough. However, but we also have this huge memory capacity at the tape and also the hard disk drive. So that's also, if you think about it, that hierarchy is also very similar to heterogeneity that you can consider. So here also you can think of heterogeneity, that so long bitline is small area and high latency. Short bitline is low latency and large area. And here the proposal is that you can make it still be a small area by using long bitlines. However, you can add try to isolate bitline using some isolation transistors, such that you can try to also have low latency sectors or region in your bitline. So by adding some isolation transistors, you can actually cause some, regions that. So if you are successfully put your data in this region of your subarray, and when you deactivate these switches, meaning that you isolate the bitline from the upper band, the upper part, your bitline is going to be shorter. So you're going to experience much lower capacitors, and you're going to have better performance. Sounds good? Okay. So if you compare commodity DRAM versus this TL DRAM, you're going to see that we show DRAM latency TRC. So in commodity DRAM, actually, the TRC is considered to be around 52.5 nanosecond. So in TL DRAM, now you have different sections. You have short, near, let's say, and also far segment. In near, you have shorter bit lines, shorter bit line, which you're going to have lower latency. So we show that we can reduce the latency by 56%. This bar actually needs to be here, somewhere here, but we are still trying to find the current plot to put here. We couldn't find it yet, but anyway, we are reducing essentially the TRC for near segment by 56%. So it should be 44. Yeah, and in far segment we are increasing the latency by 23%. Why we are increasing? Because of added isolation transistors, essentially. So those add some extra capacitors and extra latency. So if when you want to access your data in your far segment, actually you're going to experience longer latency. So you really need to make sure that you manage this structure nicely in order to benefit from it. Make sense? And in terms of power is also somewhat the same. So in the near segment, you will have lower power consumption, but however, in far segment, you're going to have more power consumption compared to commodity DRAM. So you really need to intelligently manage your data nicely. So those we're going to see different techniques that we can benefit from that. And the DRAM area overhead is also somewhat around 3% based on the estimation of this work. And that 3% comes because of those isolation transistors. And those transistors still need to be powerful. So you cannot put small transistor because they are trying to isolate the bitline. So bitline is actually relatively wide wire. So that transistor also should be powerful enough to drive the current nicely. Okay, so yeah, so with this technique, actually we are trying to be somewhere here in near segment, and we are also somewhere here in the far segment, essentially. So this substrate can be leveraged for different use cases, some different potential use. Some of them would be use near segment as a hardware managed inclusive cache to far segment. So you can consider that near segment can be used as a cache of your far segment, but this is considered as inclusive cache, meaning that whatever I have in my in near segment, they exist in far segment as well, because this is inclusive cache. You can also think of managing as an exclusive cache, meaning that you don't have repeated data. So whatever you have in what you have in your near segment, they don't exist in your far segment, essentially. You can also do some profiling and use the operating system, and use that, basically give that hint to the operating system. So because this information can be also communicated to the operating system, and then operating systems can try to, do page mapping based on this architecture, for example, for you. And also you can rely on your luck that you simply replace DRAM with TL-DRAM and hope that things gonna work well. But it turns out that it doesn't work well. So you really need to intelligently manage and use this substrate. If you just, naively replace DRAM with TL-DRAM, you're gonna actually lose performance, very likely. Okay. Yeah, so we have far segment, near segment, and we can consider this far segment as our main memory and near segment as our cache. So the first challenge is that how to efficiently migrate a row between segments. Any idea? Yes, exactly. Yeah, and row clone actually comes to play here. And makes it possible that you quickly move data from far segment to near segment, which is very important to make it effective. How to efficiently manage the cache. This can be many different techniques, like the literature in the cache optimization is quite rich. So you can also think of using many different cache management techniques, like different replacement policy, insertion policy, all these things, they can be also studied here. And this architecture also would also call for more specific analysis as well, because if you think about it, this cache is a bit different from normal caches that we have in our system. The reason is the line is actually so large. So the cache block usually is around like 64 byte or 128 byte, for example, things like that. However, here in your near segment, you have 8 kilobits of data. So managing this cache actually can be different, from the normal cache. So there are a lot of opportunity to optimize it more, by basically customizing our cache management techniques for such new baseline. But I think in this work, actually, we didn't do that much. We just used simple LRU, least recently used for cache replacement policy. And we just wanted to show, what would be the effect. But of course, people can do much more optimizations here. Okay, so we already discussed about this inter-segment migration. So basically, we need to connect these isolation transistors and then use essentially row clone to do that. So I'm basically skipping this part because I think you all are familiar with that. Okay, and for channel two, for challenge two, we, for example, did some LRU, for example, here. So here's some performance normalized. So for different core counts, and you can see that this technique can provide performance improvement compared to the baseline, and also it reduces power consumption because you increase the chance that you are operating on near segment, and that's much more power efficient. So you can also do some sensitivity analysis, like how large you make your near segment. So here you increase the number of cells, or you can also think of number of rows that you have your near segment, starting from 1 to 256, and the total number of basically rows that you have in that subarray is also 512. So when you have 256, that means that actually your near segment and far segment are actually the same, like they are not different. So by increasing the number of rows in your near segment, you are actually increasing your cache capacity, which can be useful because you're going to have better hit rate if you think about it, your cache. But at the same time, your near segment is going to be longer latency because now the bitlines are longer. So of course, again, they're going to be a sweet spot. So in our experiment, we actually get to 32. So having 32 cells or rows in your near segment provides a good balance between high capacity cache and also low latency for near segment accesses. Okay, makes sense? Yes. Yeah, of course. Yeah. It's very much depends on the workloads. So we tested on different workloads. We have you can check the paper for the list of the workloads and benchmarks that we are testing. But these works actually are enabled by simulations, of course, and that's why simulation is very much important. If you don't have simulation, you cannot do any of these works. Yesterday we had this talk in our seminar in computer architecture course, which some of you might already taken this course, or you will take this course maybe later. So one of the students, he was presenting a paper, and as a weakness, the student mentioned that this paper used simulations, which actually that doesn't sound very good to me, because what else you can do if you are changing the hardware, you're proposing a new hardware, you cannot build it. You can, but when you want to build it, you need to spend a lot of energy and cost time to build. And in the end, you're going to also build only one version of it. But with simulation, you can actually sweep parameters. You can do huge design space exploration. So I still cannot understand how people question why you do simulation, because simulation is very fundamental and very important, to enable science and science develop essentially. Yeah, some story from yesterday. Okay. Yeah, good question. Yes. Yeah. I don't have it on top of my head, but I guess there are some workloads that you get, for example, performance improvement of 20, 30, 40%, but some workloads that you get less. So on average, you're getting, for example, 11, 12% improvement. But of course, you have that variety in different workloads. You can check the paper for that detail. But yes, exactly. It's not by reporting the average number here, because I want to summarize, but we are filtering a lot of exciting information that you can get by checking each workload actually separately. Yeah. Very good questions. Any other questions? Yeah, so this the paper is going to be also part of the reading. I think you included in homework too, right? We will release homework too also. Are you guys enjoying labs and homeworks? That's a tough question. Yeah. But homeworks are easy. Like exercises are easy, no? You can easily search the title of the question and probably find a response on Google. It's not hard because these questions are, I mean, of course, would be nice if you try to solve them, but if you just want to get a correct response immediately, you can actually maybe only search some keywords of that question on Google and you're going to see. So that's why exercises are not difficult in that sense, only for the purpose of getting grade. But actually it's very important if you want to improve your understanding, if you think about it. But yeah, I mean, reviews are different, interesting, but they don't also have hard deadlines. So you have until end of January to do that. I'm not sure if you have announced also the exam. Did we do that? Maybe. So because some student actually asked me, so the exam, we will also announce it on Moodle, but just remember about it. So the exam will be on Thursday, December 18, I guess, because Friday is December 19th, if I'm not mistaken. Basically, that Thursday before Christmas, right? So that Thursday, we're going to have the final exam during the lecture time. So, and you don't need to register for the exam because we got questions about register. If you need to register for the exam, no, you don't. You just come to the exam day and do the exam. Okay. That's kind of a side question. Okay, let's move on. Okay, now, so another, I think when we were discussing about data movement, copying data with row clone and some future works on the line of row clone, Professor Mutlu, I think he also slightly mentioned about Lisa. Yes. Yes. Retention. So it does potentially, yes, I guess. Yeah. So it doesn't. So when you think about retention, there are two things here. So you don't change the cell capacitors. So that's no, you don't. However, you remember about those effects, those noise effects that was affecting the retention errors, which, when you connect the bitline, you have these noises, which you bitline to bitline coupling and also bitline to word line coupling. So now you have in your far segment and also near segment, you have a different, kind of capacitors now, right? And that can potentially affect your profiling or some retention errors that you have because of the noises. Yeah, I think that probably would be one of the reasons that we haven't. I'm not sure. I think we haven't done that experiment because for that experiment to make it useful, you need the real chip, and we couldn't build TLD RAM yet. Hopefully, at some point, DRAM manufacturer will build it, and then we can test retention time. But theoretically, I think yes. Yes. Yeah. 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 Actually, I will. Through the end, I think I will describe a paper Crow, which has done something also in that line. And one of the usage of Crow is actually for RowHammer defense. But I'm not going to go into detail of that because we're going to have lecture on memory robustness that we will describe all these techniques in detail. So, but yeah, potentially yes. Yeah. So Lisa is also another technique, follow-up on the row clone. Remember that in row clone, if you want to communicate between subarrays, actually, across subarrays, that's not easy. You cannot do it basically with good performance. So this work actually, Lisa contributes in that line and provides a technique for that, which I'm going to show you very quickly. But the main reason is that the substrate, which is enabled by Lisa, can be also used to reduce DRAM latency. And we're going to see the connection very quickly soon after. So this is the paper about Lisa. So yeah, I don't want to go over all these things. These are related to, copying data. And you can actually, you want to also copy across subarrays. So what Lisa proposed is that we provide row buffer movement, RBM, that we move a row of data in an activated row buffer to a pre-charged one. So essentially, we added some transistors again. That transistor can connect subarrays. So basically, we improve connectivity in the bank. So now you can actually connect subarrays together, and then essentially you can you do activation in subarray 1, and then you get the data in your sense amplifier and also your row buffer. And in subarray 2, actually you are in the pre-charge state, but then you activate these transistors. So now they are on. So you do this charge sharing, and then you charge the bitline. So this going to be moved to this row buffer in this subarray. And then essentially when you activate the row that you want to put the destination in subarray 2, you can copy that row to that subarray, right? It's not, again, it's not magic. So essentially you activate subarray 1, you have your data in your row buffer, but that row buffer is not connected to the row buffer of another subarray. So we add these transistors such that you can copy that to another subarray. And then by activating the row in the subarray 2, you can actually put that data as a destination to another row, which is located in another subarray. So yeah, so you can actually continue doing that, like adding more subarrays, but I mean, more connections. But actually, we did some analysis and we observed that the range of RBM depends on the DRAM design. So multiple RBMs to move data across is basically, we try to, I think, limit to 3 subarrays. So essentially 3 subarrays can do that. And if you want to do more, essentially you need to also rely on some other techniques to basically, if you want to move data from subarray 1 to another subarray which is quite far from you, you can actually do it on a multiple RBM operations, meaning that you copy from subarray 1 to subarray 3, and then since subarray 3 is connected also to subarray 5, for example, you do subarray 3 to subarray 5. So these are multiple operations until you get to the destination subarray that you're looking for. And we did a lot of spice analysis on worst case cells for that. And we observed that this is possible and provide very good performance and with reasonable area overhead. Yeah, so this can be used for rapid inter-subarray copying, as we already also discussed. But another usage of Lisa would be used for variable latency DRAM. So remember that we had this in TL-DRAM. We basically made a far segment and near segment essentially. But here, what you can do is let me actually show it. This figure is very easy to understand. So you can have different subarrays in your system. You can have a slow subarrays and also fast subarrays in your bank. And the fast subarrays are essentially subarrays that you have shorter bitlines. This baseline has been also proposed in other works, like this one, Sun Plus in ISCA 2013. But in this paper, in Lisa, we showed that how we can quickly we can enable this architecture or benefit from this kind of architecture using Lisa substrate essentially. So basically, you can use a Lisa operation to quickly communicate between slow subarray and fast subarray. And you can think of using fast subarray as your cache, and then again everything that you have seen in TLD DRAM. So you can also do here the same. Make sense? Okay. Yeah, you can also use this technique to reduce recharge latency. Yeah, okay. The way you can do is that, so the pre-charge time is limited by the strength of one pre-charge unit. So normally you have one pre-charge unit that you use it for that subarray. However, when by connecting these rows together, you can actually use, you can turn on these two pre-charge units together, and then they can drive power and they can drive current more together, more powerful. And then your pre-charge latency would be also reduced using this kind of substrate. Okay. So there are a lot more on Lisa, which you can check this paper. It's going to be also part of reading. So have you put it? Should check. Maybe we put it in homework 1. I don't know. Okay. Question. So yeah, another work is in this line is CRO, the copy row substrate. Again, the challenge of DRAM scaling is access latency, refresh overhead, and exposure to vulnerabilities, which is related to read disturbance of, for example, like RowHammer, row press, and so on and so forth. So in conventional DRAM, this is the structure that we have, DRAM subarray, and these are sense amplifiers. So in CRO architecture, we basically we don't basically chop the bit line as we do, for example, in TLD DRAM. What we do, we added another decoder. So here we have a row decoder that's used for all rows in that subarray. But in CRO baseline, you can actually have a regular decoder, which you can use for these regular rows. And then you have a CRO decoder, which you can use it as a copy rows, essentially. So you have a separate decoder only in order to access, these rows for that. And since you have a separate decoder, your latency is also lower because you don't need to decode through the high decoder, complex decoder circuitry that you have in here. Again, this is a CRO substrate, and you can use this CRO substrate in order to do some optimizations. So when you want, you can use that to, for example, to copy one row. So you make a copy in your in a CRO region of your DRAM. So you move a row from regular rows to your sense amplifier, and then map it to your copy rows, and that's your. So you have a copy of your original data, and you also in your CRO region. And then later on, for example, when you get an access, you check this in and when you want to supply the data to outside, you can actually read from CRO decoder, from CRO region and regular region together. So since you have the data placed in both regions, they can amplify and provide current to the bit line together. So you have two instances of same thing. So you can activate them separately because they don't share the same decoder. So you have different decoder. So you can activate them separately, and both of them, they provide the current for you, and those will amplify the bit line essentially together, and that can cause better performance for you. Make sense? So there are, again, use cases for CRO you can use for cache. So essentially, the row that you copy here, you can think of it, okay, that row is going to be accessed faster because I have a copy of that row, and using these two together, you can have faster accesses. You can also use that for reduce DRAM refresh overhead. meaning that if there are some rows in regular rows that through your profiling you observe that they are weak rows, meaning that you need to refresh them very, very frequently, you can actually remap those rows to your in your CRO region, and essentially read from that CRO region later on. And that can let you, for example, not refresh that frequently, assuming that rows in CRO region are strong. And also you can potentially, you can also design a mechanism for protecting against RowHammer using CRO, which I'm not going over it now, but you can also check the paper, or hopefully you're going to see in our memory robustness lecture. So basically CRO cache plus CRO refresh, actually both of them, they provide performance improvement together, 20% speed up and 22% less DRAM energy. And the hardware overhead is also reasonably low in this structure. Okay. Okay. Let's take, no, let me actually go over this paper and then we can take it. So this is another work which provides a kind of, remember that we discussed about capacity and latency trade-off, and say that essentially there is this trade-off, and you need to kind of decide, if you want to high capacity DRAM or you want low latency DRAM, because in low latency you need shorter bit lines, and by making bit lines shorter, your density is lower, and essentially you cannot have that high capacity DRAM. This work, CLR DRAM, that Hausung has done it here. He basically, we wanted to show that you essentially can reconfigure between these modes in a same structure. So you can do this capacity and latency. You can have some reconfigurability that you can morph between these different modes, high capacity mode and or low latency mode. It sounds a bit magic, but when I describe the technique, you're going to see that this is also, not that hard to do. Okay. So I'm not going over all these things again, but essentially the goal is to design a low-cost DRAM architecture that can be dynamically configured to have high capacity or low latency at a fine granularity, meaning at the granularity of a row. So for each row, we can decide if we want to have it as a high capacity or low latency. So basically the key idea is that dynamically configure the connections between DRAM cells and sense amplifiers in the density optimized open bitline architecture. So here in this baseline, we focus on open bitline, basically a structure that is actually nowadays is very common in DRAM manufacturers, because it helps to reduce, provide higher capacity or higher density. So they call it open bitline because this bitline from this side is actually connected to the sense amplifier. And from this side, this bitline is not connected to anything, for example. And another bitline that you have here is actually connected to these cells. This bitline is connected to sense amplifier 2, but from the top is not connected to sense amplifier 1. So that's the open bitline or baseline that we have nowadays actually in DRAM designs. And if you remember about Ismail's work, functionally complete Boolean logic, we actually benefit from this architecture, open bitline to do NOT operation, NAND and NOR, and all these operations that we discussed. Once you do, when you activate, so this bitline, which is connected to sense amplifier 1, actually is a NOT. And the original data of another bitline is also connected here, if you can think about it. You see the cursor, right? And that goes to another subarray. So once you activate, some row in a subarray here, you're going to have the NOT of your data in this bitline in your down subarray as well. So with that architecture, you can actually implement NOT. But as you can see that this NOT operation is not perfect, because it's not completely aligned. So you are your original data, for example, is in this location, but now the NOT is actually in this location. So you are basically shifting, your NOT operations across these cells. I mean, yeah, but that's aside because maybe you can remember now better that open bitline architecture also can be used in different use cases, different designs. Here also in CLR DRAM, we actually come up with these, again, isolation transistors. So you can actually have a transistor here, and you basically you add 2 transistors at the top and also 2 transistors at the bottom. If you have transistor type 1 both only activated, we are actually the same as the open bitline architecture, right? So there is not anything different here. But there is a mode that you can actually connect both type 1 and type 2, and then that would provide some performance improvement, which I'm going to show here. So we can have 2 modes: max capacity mode, which essentially is similar, I mean, exactly the same as open bitline architecture. You only activate these type 1 transistors. So this connection of a bitline to the sense amplifier from the top and from the down is activated. And here you don't have connection, essentially. So this is, it's not that interesting. It's very much similar to open bitline architecture. However, we can also mimic it and make it to high performance mode by activating all these connections, type 1 and type 2. And then if you store original data and also the negated value. So when you are storing your DRAM, you can actually also store the negation of that. If you store both of them, O and O bar, then you can actually, these two can work together to increase your basically power to drive your circuit. Because when you want to activate, let's see if we have a picture. Yeah, so essentially when you want to read, you need to activate this cell, and then that would affect your bitline per chip. But this cell also, if you make it as a negative one, and when you know about this architecture of open bitline, that one bitline is for negate and another one is for the original data, these two can work together to increase the current for you, and that can cause a much faster activation time. So this lower latency comes at the price of lower capacity. So you need to allocate 50% of your, essentially you're losing 50% of the capacity because you're duplicating. If you want to have this for all DRAM chip. So if you want to have the whole DRAM rows in a high performance mode, you're actually losing 50% capacity. But it's also very, that trade-off has been used in other memory technologies as well. Like for example, in flash memory, we have a single level cell, which you can store only 1 bit in each cell, and that provides very good speed up for you, like high performance access. But you can also store multiple bits. You can store, for example, 2 bits or 3 bits in your NAND flash cell, and that provides better capacity but lower performance. So that trade-off between capacity and latency actually has been studied in a reconfigured way in flash memory, for example, because you can actually, we're going to see in our lectures in flash memory, but you can actually do it at runtime. You can change between SLC mode and MLC mode at runtime. So you can actually configure and play with that trade-off at runtime. But in DRAM, actually, that wasn't possible, right? Because, but with this architecture, you can actually play with that trade-off here as well. Okay, so there are some results here that we basically, for the performance activation latency, we reduced by 60%. Restoration latency also has been reduced, pre-charge latency, and write latency recovery. And overall, this comes at system level benefit, around 19% performance improvement, around 30% energy reduction, and 66% DRAM refresh energy reduction. Question? Okay. Let's have 11 minutes break until 3:20, and then we will continue with SALP. This is very exciting work. Okay, let's continue. I hope I'm still audible. You hear me, right? Yeah, so this is, I think it's gonna be the last work I'm gonna present in the line of the first, reason that why we don't have low latency DRAM. And this work is very exciting, very fundamental, and I think it's one of the first paper. It's not the first paper I've read from Professor Mutlu, but it's one of the first paper I've read from Safari before I joined this group. I joined this joined Safari in 2017 as a visiting PhD student. Back then, I was working, doing my PhD thesis on GPU microarchitecture, improving memory system. And I was quite excited about the works that Safari has been doing. So I was checking a lot of papers. This paper was one of the papers I read back then, but it's not the first paper I read. The first paper I will discuss it later in the flash memory lectures when I get to that, hopefully. But yeah. So this paper, SALP, we also kind of, you also the key idea, I think you have seen it a little bit yesterday when we discussed about this access refresh parallelism, that we wanted to parallelize between accesses and refreshes in DRAM. But SALP is actually more than that. Is talking about access to access parallelism. So essentially, you can provide parallelism across different subarrays. Actually, SALP stands for Subarray-level level parallelism. So the name actually can give you some idea what is it. So the problem, goal, and observations, I will go over it quickly. Bank conflicts are costly for performance and energy. So normally, so in DRAM architecture, we have, as you remember from our pictures, several subarrays are inside one bank, and they are sharing actually the same decoder, row decoder. So essentially, when you want to access, when you are accessing a subarray, you cannot service another accesses which can go to another subarray actually. So you basically, even though these subarrays, actually different subarrays, they have separate row buffers, which potentially you should be able to, activate different subarrays in parallel. But the circuitry that you have, the interfacing, does not allow that. So essentially, you have limited parallelism, and that can comes at the problem of bank conflicts, that you have several requests going to the same bank, and they are going to the different subarrays, which you can potentially service them, but you cannot because of the interfacing. So basically, this work focuses on reducing bank conflicts without adding more banks. So of course, you can add more banks. That's one solution. But by adding more banks, actually, that's a let's say heavy solution to this problem, because you need to add a lot of circuitry interfacing for doing that. So the first observation is that a DRAM bank is divided into subarrays, and each subarray has its own local row buffer, which I already discussed it. And so the key idea is actually based on also the second observation, that subarrays are mostly independent. So basically, except this global decoder, that they are sharing global structures to reduce cost. So key idea of SALP is that minimally reduce sharing of global structures, and also global row buffer, which we should not call it actually row buffer, global row buffer. We have local row buffer per for each subarray, but this structure here, as if you remember from this lecture, I talk about it, bank I/O or global I/O circuitry, is not actually a row buffer. So we should not have done it also in the SAT paper, I think, but that's how it is. We call it a global row buffer, but remember that it's not global row buffer. It's a global bank I/O. So key idea of SAT is that, and so basically we reduce sharing of global decoder that enables almost parallel accesses to subarrays. And this global circuitry, global bank I/O, we reduce the sharing of that to utilize multiple local row buffers, essentially. Essentially, we allow that different local row buffers can quickly switch. Basically, this bank I/O, the global bank I/O, can be quickly connected to different local row buffers, which you're going to see now. So that's the idea for SALP. So instead of a global latch, so there is this latch circuitry that you provide the row address, and then you latch this address, and this address will be used in order to access your subarrays. So why do you have a latch? Because you need to make sure that there is no, let's say, noise in that. Because usually combinational circuits can be noisy. You might have a lot of glitches in combinational circuits. So you provide the address to the global decoder, and then you latch it. You latch it to make sure that that address is stable, and I can work on it. And unfortunately, there is one global latch which is shared across all these subarrays. So you can actually, instead of having one latch, you can move this latch across different subarrays. So you can think of, for each subarray, I can have a separate latch, just to latch the address. So with that, you cannot provide addresses for different subarrays immediately at the same time, but you can concurrently, you can concurrently provide that address. So you, for example, provide the address for the blue subarray, and you latch it, and then you provide the address that you want to access for this and for this yellow subarray, and you latch it. Make sense? So that's the way we try to break the dependency at the global decoder. And so with that, you can potentially provide the parallel accesses to the subarray, and they can read and essentially activate and have the data in your local row buffer. But there is also another problem here. So in normal operations of the DRAM, like in conventional DRAM architectures, this local row buffer, only one of them can be connected. So one row buffer can be connected to the global I/O, and other row buffers are actually, you can consider that they are not connected because they are actually pre-charged. So normally, they are pre-charged, and there is only one local row buffer which is not in a activate mode, and you can actually connect it to the bank I/O. However, in this scenario, you might have multiple local row buffers that they are valid, and they need to be communicated to the basically this global bank I/O. So essentially, you need to add again some switches. So you have some switches, and then you can control by using designated single bit latch. And so using these latches, you can actually control which row buffer is connected to these global bit lines. And that can also break the dependency there to say which local row buffer can be connected to the global bit lines and move to the global bank I/O. Make sense? So that is SALP. And if you think about it, actually, it can provide very good performance. For example, imagine that you have these consecutive accesses, read A and read B. Like these are different rows, and normally, the row A actually is stored in one subarray, and row B is stored in another subarray. So in conventional DRAM, in order to access row A, you essentially go to the subarray that has row A. You basically activate and move the data to your local row buffer, and then provide the column address and read your data. However, since the next request is actually for another row, which is B, and B is in a different subarray, you actually need to close that subarray. So you close that row, meaning that pre-charge that subarray, and then you activate another subarray. So you need to do this activate, pre-charge, activate, pre-charge all the time in order to address these read A, read B, read A, read B, for example, access patterns. However, with this kind of architecture, SALP, you can you provide read A, so you provide the data in local row buffer, and also provide read B when you have it, and then it's also provided in local row buffer of this, and then addressing A and B is just a matter of switching. You just quickly switch across these different subarrays, that which one can communicate with global bitlines, and that switching is much faster compared to closing the subarray and activating again that subarray, and that's why SALP actually provides good performance for you. Make sense? Okay. Yeah, I think I already described all of it. Yeah, and this is the proposed SALP. Actually, in the paper, if you check it, which is going to be also one of the readings in the homework, you're going to see that there are different versions of SALP. And the one that I'm describing now actually is one of the most optimized and let's say ambitious way of implementing SALP. It's more complex, but provides also the better performance. So the overhead of SALP in DRAM chip, based on our estimation, was around 0.15%. But this actually is a bit higher. Maybe something around 2%. If you are not careful in designing, might be also a bit more. But overall, it's not a it's not a technique which is high overhead. So this can be actually implemented. And I will also share with you some story through the end of these slides. That actually there were a lot of discussions on DRAM manufacturers that they wanted to implement SALP, but yeah, you can wait for that. So for the results, basically SALP provide DRAM energy reduction and provide good performance. So here, different versions of SALP and also the ideal. So in ideal scenario, we consider that basically you have like each subarray is a bank, ideally. So in order to have zero bank conflict, subarray-level conflict, let's say, you can consider that each subarray is a bank. So you ideally increase the number of banks to make sure that you can actually address all these subarray accesses in parallel, essentially. So that's the ideal case, which is exactly, which you can imagine how costly it is. But the ideal case actually can provide on average only 20% performance improvement. And with this SALP, we provide 17%. So it's in the margin of only 3%. And like you can see that the cost is much lower compared to that ideal case that you can envision, but the performance improvement is very much in the margin of that. Okay. So this is SALP. And interestingly, also in this paper, which I also discussed it yesterday. Yesterday, I talked about one story about this paper that people from Samsung and Intel, they wrote this paper together. But they actually, in this paper, they also discuss about SALP paper, Subarray-level parallelism. And so they wanted to use Subarray-level parallelism for another reason. They discuss about the latency for write restoration. They wanted to increase that latency and make it more relaxed to make sure that the reliability of the subarray is better. But that would come at the price of performance overhead. And they show that with SALP they can actually fix that performance overhead and provide that relaxation of TWR, which is good for reliability, as they discuss in this paper. But at the same time, also they have similar performance and potentially better performance by using SALP. So that's why actually these people, yeah, here also discussed it how they use SALP and this right restoration relaxation. And actually, the version of SALP that they actually implemented in this work is actually not the most effective or optimized way of SALP. I don't exactly remember which version was that, but it's not the one that has everything, which with 17% improvement, which I reported. Yeah, so essentially, there were a lot of discussions in the standard community as JEDEC, that essentially these people from Samsung and Intel, they really wanted to make SALP implemented in real chips, but in the end they lose the the discussion in that JEDEC politics essentially. So in the end they couldn't implement it. I think actually SALP at some point will be implemented because it's not a high overhead technique, and it's very much important to have. And but yeah, I don't know. Maybe we should wait to see when they were gonna do that. Question. Okay. So with that, I think we conclude reason 1. For the rest of today's lecture, I will start going over reason 2. That one size fits all approach that we have. So that if we try to be more intelligent in how we manage that, as we also did in refresh lecture, we show that not all cells need to be refreshed at the high refresh rate. So similar thing also exists here. So you don't need to, so not all DRAM rows need to be that long latency. Have you guys have done this overclocking memory for gaming? Maybe you don't play video game. Not in your high school also. Yeah, I remember actually, I didn't do that also, but I had colleagues that they were doing this overclocking, just magically consider that, do overclocking and access the main memory faster. And that can, provide much better performance for game, but at some point, that could also come at the price of low reliability. Sometimes, they just crash. Hopefully they save before that crash, but but then that can happen. So people also, have that intuition also that DRAM actually the latency that is dictated by these manufacturers and memory controller is obeying those latencies. We can actually potentially do much faster with that, and nothing will happen. But if you don't do it carefully and you don't have good methodology on it, then you might also run into issues like low reliability also, which you should be able to handle it essentially. So a lot of ideas that I will discuss in reason 2 is going to be around that kind of methodologies. So basically, we want to tackle the fixed latency mindset. Reliable operation latency is actually very heterogeneous across different temperatures, different chips, parts of a chip, voltage levels, and so on and so forth. So the idea is that to dynamically find out and use the lowest latency one can reliably access a memory location bit. I'm going to discuss about different works, which I think we're not going to have time today to go over all of them. So the rest will be covered hopefully next week. So basically, we would like to find sources of latency heterogeneity and exploit them to minimize latency or create other benefits that you're going to see in this lecture. Question? Okay. So we have a latency variation in memory chips. This heterogeneous manufacturing and operating condition that cause latency variation in timing parameters is very similar also to refreshing. Because of the process variation, you're going to have heterogeneous, latency in your system. So here is the DRAM latency that, for example, in your, scale can be so low and can be high. And different DRAM chip actually can have different profile. Like DRAM A can be actually around this low latency DRAM B can be around this, and DRAM C here. And this is actually real. Like if you profile DRAM chips, you're gonna see different latencies. However, and even in each DRAM chip also, you're gonna have different kinds of cells. We're gonna have heterogeneity across them. Yeah, but however, usually, basically the DRAM manufacturers, they put the standard here, for example, so just to make sure that all DRAM chips, they work. And that's clearly that's a kind of business decision, because they want to have high yield for that. Because if they have a standard latency, which is, for example, somewhat here, then that means that DRAM B and DRAM C are not functional, right? They need to throw it away. So they have lower yield, which in the end, they're gonna recover that by increasing the price for each DRAM chip. Which in the end, the end user, we're gonna need to pay more. So it's not, well, if you think about it, that can be also from their market, because when they provide higher price for their product, then they may at some point lose the market as well. So it's a back and forth problem. But essentially, I think we really need to push for better standard, having a much lower performance, or actually come up with this kind of heterogeneity techniques that you operate on with each DRAM with its latency that it has, based on its profile. Okay. So why is latency high? DRAM latency, which we already also discussed, is specified by the DRAM standards. So that doesn't reflect true DRAM device latency, and it's because of the imperfect manufacturing process. So we discuss it, and then we have this standard latency, that high standard latency chosen to increase yield of the DRAM. It's not only for DRAM devices, also if you think about it, many chips are also like that. Manufacturers try to have quite high yield to sell more chips as much as possible, and that can also contribute to have a lower price for their product as well. So I don't know. So end user can be happy or not happy here. As an end user, you can be happier if you have faster DRAM, but you might have to pay more, if that faster DRAM comes at the price of lower yield for them. Think about it. So what causes, we were discussing that. So basically we have these conservative timing margins, and the DRAM timing parameters are set to cover the worst case. Worst case temperatures, like 85 degrees versus common case. I'm gonna show you some analysis that even though these numbers are tuned based on 85 degrees, but we rarely actually get to that temperature. So in general purpose computing, in our personal computers, actually DRAM operates around 50 degrees, for example. In servers, actually DRAM operates on much lower temperature because of the cooling technique that they have. It's actually around 27 or so. So you can see that normally we actually operate DRAM on much lower temperature, which can potentially, enable you to have lower latencies. Also, they consider based on worst case devices that DRAM cell with smallest charge across any acceptable device to tolerate process variation and so on and so forth. Okay, and overall, all these leads to large timing margins for the common case, which you have huge slack, which now we can actually work on it for optimizations. So we did some work to understand and exploit them. So here is again, overview of DRAM structure, which I'm not going over it again. DRAM cell, sense amplifier, and 3 steps for essentially sensing, restoring, and pre-charging. So yeah, so here is your cell and your sense amplifier, which is pre-charged. And then, okay, so here you can consider, you have high value, which you encoded as 1, and low voltage, which you can encode it as 0. You always need to consider some margin because of our noise. These are noise margins. So sense amplifier is actually like the bitline is pre-charged to half VDD. And then at some point you basically connect the cell to the bitline, and that will cause the bitline to have gain some charge, a bit more than half VDD, and then you enable sense amplifier to restore this charge, to make it to 1, and then you restore it. So in theory, here I should be able to, access my cell. In fact, actually, we should be able to access cell even earlier than that. We don't need to wait for 100% restoration. Usually, people can do start accessing after 80% restoration. Make sense? But in practice, actually, we have somewhat here. So there are 2 reasons: process variation and temperature dependence. We already also we discussed actually about both of them. But here I can actually provide also a bit more. So ideally, the DRAM should be like this: that all DRAM cells have same size, same charge, and same latency. But in practice, we have different cells, different size, different charge, and in the end, different latency. So we will have large variation in cell size, smallest cell and largest cell. So when your cell is small, meaning that the capacitor is low for that cell actually stores much lower charge. So when you connect that cell to the bitline, since for the first procedure, which is charge sharing, that capacitor cannot provide enough charge for you. The current is limited. So that's why actually the procedure for a smallest cell is actually lower. Like you have a longer latency when you do this charge sharing. Whereas for larger cell, you have higher capacitors. Basically, in larger cell, you have more charge stored in your capacitor. And that more charge actually can lead to faster charge sharing procedure, for example. And that can contribute to faster latency for you. There are other things also, contributing here, like the access transistor, which are also not ideal. So some of these access transistors are faster, some of them are slower, and those can be effective. So there is large variation in cell size, which cause large variation in charge, and that can cause large variation in access latency. And in process variation, also, if you think about DRAM cell, so this picture is more kind of real, the way that manufacturers build DRAM cells. So you have a DRAM cell, and then you have this contact. So you can actually have variation in all of these. So cell capacitance can be different, contact resistance can be different, and transistor performance can be also different. So all these will, contribute in different latency. I think I already discussed that. Okay. And with temperature dependence, so DRAM, so we know from our actually yesterday lecture that in higher temperature, actually DRAM leaks more charge. So that's one thing. And also temperature it leads to extra timing margin for cells that operate at low temperature. Okay, so yeah, we usually, so we can operate at room temperature or hot temperature, which is 85 Celsius. If I also want to give you some insight here, 32 nanosecond, which I discussed, sorry, 32 millisecond, which we discussed about it yesterday, was the refresh rate which you need to have for normal, let's say, temperature of your DRAM. When your DRAM is actually, the temperature is higher, you need to increase it. At some point, you need to, around actually above 85 degrees, you need to actually refresh your DRAM at, for example, at 16 millisecond rate. And even higher than that, around 110 or so, you might need to refresh at 8, the millisecond rate. So there are a lot of interesting, study about that, and actually observing the retention time based on the temperature is actually easy to predict and model. But we also have the same, profile. I mean, somewhat similar profile for timing. So DRAM timing parameters are dictated by, like they can be different when you have different temperature. Okay, so yeah, we already discussed about all these. Like we are always based on the worst case, like all DRAM products and with different temperature, they should be able to work at some timing parameters. But we know that depending on the chip that we are using and also the working temperature, we can actually have different latency profile out of the DRAM. Okay, so this work, adaptive latency DRAM, the idea is that to optimize DRAM timing for the common case. Basically, considering the current temperature and current DRAM module we have. So we already discussed that. Why would this reduce latency? So I'm gonna skip this. Okay. So this is something that I wanted to talk about it. I mean, I described it also a little bit, but extra charge that you can have in your cell capacitor can actually cause reduced latency for us. So it can contribute to lower sensing latency because that extra charge, you have more charge in that cell and that can provide more current for charge shading, for example. Restoration also can be faster, again, because of that. And also because the fact that when you are doing this charge shading, that cell doesn't lose a lot of charge when it has enough charge in it. So you need to spend less time to restore it. And also a similar idea about why it can contribute to for pre-charge. So no need to fully pre-charge bitline for cells with extra charge because they are more powerful, essentially. So we did a real experiment using our infrastructure. Here, actually, in this work, SoftMC. And later on, as you know, we actually extend this work, and now we have DRAM vendor infrastructure. But fundamentally, they are also, I mean, they are using this FPGA-based infrastructure. Okay. So yeah, these are SoftMC and DRAM vendor papers. If you're interested, you can check. And we tested across different DRAM products. So we made several observations. So the first one, which I'm going to show here, is that we can have basically faster sensing, so more charge, meaning that we have a strong charge, and then you have a higher flow. So that would, incorporate to faster sensing. So we observed that actually across 115 DIMM that we have tested, basically the timing, which you can actually summarize it by TRCD, can be reduced by 17% on average without observing any error. But if you actually pick each DIMM separately, which we have the data in the paper, actually, you can check. There are some DIMM that actually you can reduce the timing by maybe 40%, 50%. Some DIMMs that you can reduce less, but on average we have this 17%, reduction in TRCD without any errors. Okay, so this can be also interesting, no? So you go to market and you buy a DIMM, but you can be lucky and your DIMM is faster, than other people. But then if that happens, probably manufacturers are gonna price that DIMM more because they always want to make money, I guess. Okay, and also we show that we can reduce restore time, essentially with using this technique. So TRAS for read actually can be reduced by 37%, and for write restoration also can be reduced by 54% without any errors across all these DIMMs that we checked. So yeah, this is the work ALDRAM, that the key idea is to optimize DRAM timing parameters online. And there are two components. DRAM manufacturer provides multiple sets of reliable DRAM timing parameters at different temperatures for each DIMM. So that's so here we actually input that information from our profiling. But ideally, for example, if you want to implement such techniques, a manufacturer should provide that latency profiling. For example, say that if you are working at the temperature between 20 Celsius to 40, these are the timing parameters. If you're operating at something between 50 to 85, here are the timing parameters. And if you have that kind of information per module, So that information should be specific per DRAM module. Then you can actually benefit from such techniques. And so another component of ALDRAM is that you monitor your system. Basically, you monitor DRAM temperature. And we use the DRAM timing parameters based on the temperature profiling that we have. Yeah, so here actually what I was talking about today, like DRAM temperature, we have done actually, we measure temperature. In server cluster, actually, they usually operate at under 34 Celsius. And in desktop, actually, they operate at under 50 degrees Celsius. However, in a standard, actually, they are optimized for 85 degrees Celsius. So there is huge ways here that we can optimize. Okay. Prior work also have shown that about this kind of different temperature. Okay. So yeah, here are the results for latency reduction for read and write if we operate at 55 degrees. Of course, I mean, these are the basically we input through our profiling through that 115 DIMMs that we had. So for read latency, we reduced by around 33% and write latency by 55%. And so per timing, sensing latency actually has been reduced by 17. Restoration for read 37%. For write restoration is 55% and pre-charge 35% general. Okay, and we did actually also that we evaluated using a real system. So it's always good that if you are able to do it or evaluate your technique in real system, you should do it. Here is a system we use. So there is a possibility that you can actually change the modify the timings that memory controller operates on it by programming the BIOS essentially. And so basically we change these parameters in the BIOS based on the temperature, and then we actually run different applications from different benchmark suites. And here are real results that we get from our work. This shows a single core that average improvement for non-intensive applications is on average 1.4%, and for intensive applications is average is 6.7%. In multi-core, actually the results are much better because the problem is going to be much more important because in multi-core you have more essentially access to the DRAM, so you have more blocking. Time to time your channels, they cannot provide enough bandwidth for you, and many requests are waiting for each other. So once you reduce some latency, you can basically service some of these requests faster, and that can contribute in lower depths in your queues, and that would reduce the blocking time which you might have in multi-core system. So in multi-core, we observe actually higher performance improvement using such techniques. Okay. Yeah, I think we already discussed this about the summary results. So let's conclude with some advantages and disadvantages. So this simple mechanism to reduce latency and significant system performance and energy benefits, and benefits higher at low temperature and also when we have multi-cores, low cost and low complexity. But of course, it has some disadvantages. For example, need to determine reliable operating latencies for different temperatures and different DIMMs. So that's essentially the profiling overhead that you have here. So yeah, but this might not be that difficult for low temperature. So there's more on this paper. If you are interested, you can check. It's going to be also one of the suggested, I guess, paper in our homework too. Okay, let me see. I think I will continue a little bit until I get to I will get to a nice cut soon, and then we can depart. So ALDRAM exploit latency variation across time and across chips. And now the question is that, is there also latency variation within a chip? And we already know that, yes, across different parts of a chip, we have, different latencies. And I arrive to the actually to the nice cut. So the rest I will hope we will pick up next week. We're going to talk about how we can benefit, how can we exploit the heterogeneity that we have across different parts of a DRAM chip. And yeah, by using that, you can also improve performance even more. Question? Yeah, we are actually very on time. So then I guess have a nice weekend and see you all next week. Thank you.